Okay. Okay. So welcome to the first colloquium for spring 2025. Uh, I have the pleasure to have Paul Musial. Well, he participated in our seminar several years ago when it was not digital but in person. And he's now, we have the privilege to have him as a join at Roosevelt University. And he is member of the Calderon Sigmund Schools. He graduated at University of Illinois at Chicago. And he is going to talk about integration, Riemann integral, and I don't remember the title. Can you share the
Yeah,
title?
I'm ready. I'm ready. Yeah.
The screen, please. Okay, good. Okay, so from Riemann to Lebesgue and beyond, in investigation of a powerful new integration technique and some application. Thank you very much for your participation, Paul.
Thank you, and thank you for the introduction. Can you hear me okay?
Yes.
If I ever get any shaky internet, let me know right away, and I'll switch to another. Sometimes the Comcast here is a little shaky, but if I ever come in and out, please let me know right away, and I can go to Plan B. Okay. All right. So my road to Roosevelt. Give me a second here. All right. So I can just embarrass Wilfredo. So this is the conference where we honored Yoram Sagar around his 75th birthday. He's there in the middle. So on the far left is Valley. I don't know if Valley's here. I know he's on the invitation list, right? Wilfredo,
I invite him,
yeah,
but
yeah, he's always invited, so I don't know if he comes. Calixto Calderon is next from UIC. And on the far right is Michael Zwickel. Wilfredo, I don't know the other two. Who are they? Do you know? You're muted.
uh,
Do you remember?
yeah, she is from Florida International University.
Yes, right.
I, I don't remember her name now. I'm sorry. I should, but we are getting old.
Yeah.
And the other guy I don't remember.
Yeah. We had about, I don't want to say 50 people there. Now this is Yoram Sagar. So uh, this was my PhD advisor. Now Wilfredo's was Gene Fabes, and Gene Fabes and Nestor Riviere at Minnesota and Yoram were very, very close friends. And I just never heard I never heard the end of the two of them. So they were he always sang the praises of Gene Fabes and Nestor Riviere. We spent a lot of time together, Yoram and I, working on my thesis, and then later on a paper that never eventually got written. But we spent a lot of time together, and I'm eternally grateful for all that he did for me. I really, really, very much appreciate all that he did. So, without further ado, let's do some math here, right? And what do I do here? So this is joint work with Valentin Shpatsov, Piotr Swarovski, and Francesco Tulone. Francesco Tulone is on the left here. And Francesco Tulone is hoping to come to Chicago next fall, and hopefully he'll give a colloquium if all goes well. I mean, that's the plan anyway. And here we are eating pizza in Sicily. He's from Sicily, and he never let me pay for anything. So I did not pay for this pizza. So he was a great host, and I'll try to return the favor when he comes in the fall. And he's one of my three co-authors. He and I first met in Budapest in 2013 at the Real Analysis Exchange Summer Symposium. I don't know if you guys have ever heard of that, but it's a wonderful meeting that happens every year. It's been in Europe most of the time for the last couple of years, but it was in Łódź, Poland this year. and I got to meet one of my colleagues there. I think it was very important for me to branch out and to work with other mathematicians. So in 2013, we started working on a paper, and then eventually we started working with his advisor, Valentin Shkvatsov, and then finally with Piotr. So now the four of us are working on several papers and a book. All right. So these are the papers that we have been working on. And I forgot to change this. It has actually, this is not just submitted, this has been accepted, the first one. And the bottom one is still in the submission process. All right. So what are we going to be talking about? Quite a lot of stuff here. So I'm assuming everybody here has some familiarity with the Riemann integral. I know that some of fellow students might be here, and so if you either have thought about the Riemann integral in the calculus setting, where you think about the Riemann integral as essentially the limit of Riemann sums, then this should be quite familiar to you. We're going to talk about many new different types of integrals, some of which are from the early part of the 20th century, and some of which are more recent. And then we'll talk about some more recent results that I'm responsible for with my co-authors. All right, so got a lot to do. Let's get started. So this is a notion that we have from calculus. Okay, we take a bounded interval and we partition it into subintervals. These intervals are non-overlapping. They touch each other. They don't have to be the same size. I know that all the time, often in calculus, we'll just say, oh, they're all the same size. They don't have to be the same size. So, and the norm of the partition is simply the maximum of the lengths, right? So what's the definition of the Riemann integral? We often think of, when we take an integral, we say, oh, we're just finding a derivative, right? Well, it's not quite that simple, because actually the Riemann integral doesn't integrate all derivatives. So you have to be a little bit more specific than that. So this is our definition of the Riemann integral. I don't know if the students will get to it in the analysis course, but this is basically something that is talked about in calculus. So either calculus 1 or calculus 2. So what are we doing here? We have this function, we form a partition, and we say that, so the epsilon is basically an error, a sort of a vertical error. And we say that the function is Riemann integrable with integral L if for any epsilon there exists this this number, it's a number here, which we call the norm of the partition, say, and we'll say that, hey, you know what? If we take any collection of any partition of the interval a to b, the xi's, these are xi's or xi's or elements that are in the interval from xi minus 1 to xi. We make sure that the xi minus 1 never exceeds delta for any, so it's a fine partition. And if this holds, we say we have Riemann integrals. I'll just assume that you guys have some familiarity with that. All right. No, the answer is no. And I cooked up a little example here of an example of function which is not Riemann integral. So just have a look at this here, right? We're taking x squared, which we all are familiar with, the parabola, but then we multiply by sine of pi over x squared. Now, of course, that's not defined at 0, so we'll define f of 0 to be 0. And let me make sure hold on a second here. Sorry. I just have to, hold on. I'm sorry. Stop sharing. I want to pull this thing up. Hang on a second here. Oh, I have to stop sharing. Never was really very good with the Zoom here. Okay. Can you see this? Can you see my decimals? Okay, perfect. Okay, guys. I don't know. I love decimals. I can't tell you how I can live without it. All right. So what I did was, I here have the function, right? That's what's going on here. So what's going on here? So this is the function, and it's not really that interesting. What's interesting is its derivative. So what I'm going to do here? What's it? I have to hit the house here, right? So what I do want to do is, I just want to put this guy away for a second. Here we go. So I want to point out that my function, which is up here, x squared sine of pi over x squared, is sort of trapped between x squared on the top minus x squared on the bottom. And I do this, I'm going to show you this because By the squeeze theorem, which you guys study in calculus, this function must have a derivative at 0 because it's squeezed between x squared on top minus x squared on the bottom, right? But the interesting thing is the derivative. So let me go ahead and show you the derivative. Now the derivative is crazy like this, right? So that's why I used the slider to kind of show you that, right? To show you what happens with the derivative. So the derivative is pretty clearly unbounded, even though I can't show you all the way to infinity. It's unbounded. But not only is it unbounded, right? If I take this derivative, and I'm not going to do the whole schmear here because it's really hard to figure that thing out here. But, right? And not only is it unbounded, but if I take the positive part, just the positive part, the part that's above the x-axis, and I take the positive part and I integrate that with respect to the Lebesgue integral, which I'll talk about in a minute, I get infinity, and same for the negative part. So this derivative is not even Lebesgue integral. It's not Riemann integrable because it's not bounded. I'll explain in a second why. That's very important. The Riemann integral function has to be bounded. Okay, right? Can you see my slide again now? I have to I'm not the greatest navigator on Zoom here. Okay. All right. Does the function need to be continuous? No. You can, have a handful of discontinuities. And we study in calculus many cases where a function might have finitely many discontinuities. We know that's okay. But actually, it can have countably many discontinuities as long as they're kind of spread out a little bit. But it cannot have too many. It can't have uncountably many discontinuities. Does that need to be bounded? Yes. And the answer of why is just a brief discussion here. Yeah, the reason it has to be unbounded or cannot be unbounded is because, well, right, if it were unbounded, you simply kind of take your interval, cut it in half. It has to be unbounded on one half or the other, if not both. And then you say, okay, maybe it's unbounded on the right half. Now take that interval, cut it in half, it has to be unbounded in one of those. We keep squeezing, squeezing, squeezing down, and we get a single point. And at that point, the function is unbounded in any interval containing that point. And now, no matter how small your gauge is, no matter how small your delta is, you're going to be able to choose, since the function is unbounded, you're going to be able to choose the function value, f of psi, to be arbitrarily large. And so you can make the integral take on arbitrarily large values. And that is not something we want. Or arbitrarily negative. That's not something we want in an integral. So you cannot have an unbounded function be Riemann integrable. So there's a number of ways of addressing that issue, right? One of them is to have a slightly different definition of the integral that simply takes the gauge, the number delta, and replaces it with what we call a gauge, which is a delta of a function, delta of x. It's a positive function, and we'll call it delta of x, right? And we'll say that a tagged interval, I'm sorry, a tagged interval is an interval, and x is an interior point. It has to be either inside or around the boundary of that. And we say that that tagged interval is delta-fine if the interval lies in this open interval here. So it just isn't any. The gauge is like gauge of railroad tracks. It doesn't let you vary too far away. Okay. If you have a whole partition and all the intervals are delta-fine, which means they have their little tags, and all the intervals are delta-fine, we say that the partition is delta-fine. Okay. Now, there's a very interesting question that comes up, and that is that, well, what if I make my gauge super small? Is it possible I make my gauge so small that I cannot even find a delta-fine partition? Answer, nope. Even in the 1800s, it was known that that can't happen. No matter how you define your gauge, you can always find a partition which is delta-fine, and that's called Cousin's lemma. I think Cousin was Belgian or French. But it's the proof is exactly like what I just told you about the reason that a function that's unbounded can't be Riemann integrable. Namely, if there were no partition, there would have to be no partition of one half of the interval, and then you keep going, and you just run into a contradiction. So it's basically just a compactness argument. All right. So, okay, this guy here is the Riemann integral. And this is a new integral called the gauge integral or the Henstock-Kurzweil integral. And I know that's a lot to read, and you don't study this every day like I do. So what I did was I put the Riemann integral and this relatively new Henstedt-Kurzweil integral. We're talking about the 1960s here. It's not that old. Together, and the differences are essentially one's in red and one's in blue. Instead of a number delta greater than 0, there's a gauge delta of x. And so that gauge can vary depending on the value of the x. And when we say in the Riemann integral, we say that the having a norm less than delta, well, but remember the norm, that's a number. So that means that all of the intervals has to be less than that number. So what I want is for the Henstedt-Kurzweil integral, I want delta fineness. Remember, delta fineness means that the width of the interval isn't less than or equal to a particular value delta that's uniform for all of them, but it is local, depends on the various value of x. Okay? Other than that, the definitions are pretty much the same. All right? In fact, Riemann integrability is simply Henstedt-Kurzweil integrability when that gauge here can be chosen to be a constant. Right? I'm not going to prove it, but one of the huge advantages of the Henstedt-Kurzweil integral is that it integrates all derivatives, even if they're unbound. Okay, the Henstedt-Kurzweil integral integrates a lot more functions than the Riemann integral because it's a lot easier for a function to be Henstedt-Kurzweil integrable. Right, you don't have to check as many gauges, as many possible intervals. Right, and I've already shown you a picture of the derivative of this guy. Right, turns out that the derivative of this guy, let's call it f prime, whatever, is Henstedt-Kurzweil integrable, even though that derivative is not Lebesgue integrable, and certainly not Riemann. Okay. Now, why don't we all study the Henstedt integral or the Henstedt-Kurzweil integral in graduate school? In Will Ferrell's class, you guys may be able to get to the Riemann integral, but you certainly are not going to be studying the Henstedt integral. You can't do everything. And most of us who went to graduate school studying math, we studied the Lebesgue integral in many applications, the Lebesgue integral. Why is it that we study the Lebesgue integral, even though the Henstedt-Kurzweil integral is more general? Well, the answer is partially this. Lebesgue integral is an absolute integral, right? So if a function is integrable, then its absolute value is integral. Okay. Now, that's really important. In fact, that's baked into the definition because really what you do is you define the Lebesgue integral for non-negative functions, and you say that a function is Lebesgue integrable if both its positive part, the part above the x-axis, and its negative part, the part below the x-axis, are both integrable. And then you define the integral to be the integral of the positive part minus the integral of the negative part. Well, if one of those is infinite, then you don't get integrability. It's possible they could both be infinite, however, the positive part and the negative part, right? The Henstedt-Kurzweil integral takes advantage of the sort of the cancellation, the oscillation, but the Lebesgue integral doesn't do that, right? Another reason that we're probably not going to see the demise of the Lebesgue integral anytime soon is because that the Lebesgue integral is well adapted to arbitrary measure spaces. So it's just not the case for the Henstedt-Kurzweil integral. So there's a lot of things that are true for the Lebesgue integral that are not necessarily true for the Henstedt-Kurzweil integral. Dominated convergence. There is a dominated convergence, but not quite as powerful as the very, very important dominated convergence. There's a lot of limit theorems that hold for the Lebesgue integral, but then when you open the door to other integrals, things don't work quite as well. There's not a wonderful norm. There's no complete measure space. There's no complete metric space. There's a lot of things that don't work that do work for the Lebesgue integral. So Lebesgue integral is not going, right? Now, most of you guys, even if you studied the Lebesgue integral, right, you probably have never heard of what I'm about to tell you. And that is that, if you actually study the Lebesgue integral, usually what you'll do is you'll study measure spaces, the measure of a function, measurable functions, measure of sets, and so forth. And then you'll talk about simple functions. You'll define the Lebesgue integral of simple functions, and you have a bunch of limit theorems that will get you to the case of not simple functions. Simple functions are just characteristic functions of measurable sets times constants, add them up. So they're just, they have finite range. They have finite range. So then you take limits to get to the general case. However, in 1960, right around the time the Henstedt was working, the McShane integral was developed. McShane showed that a function is Lebesgue integrable if and only if it satisfies the following condition. Well, what's the difference? I'm seeing a gauge, right? I'm seeing this difference here. Well, what's the difference? Okay. The only difference is that when we talk about a tag partition, we require that the point where you evaluate the function is inside the interval. We require that, of course, for the Riemann integral as well. Here we say, nope, nope. All we require is that the interval xi minus xi uh, is no more than delta of xi away from xi. So that means that the point could actually be outside the interval. Amazingly, amazing. I still am shocked. The Lebesgue integral is equivalent to the McShane integral. This actually defines the Lebesgue integral. Well, there are more things that you have to check here because, right, for the Henstock-Kurzweil, you only have to check tagged intervals. And here you have to check sometimes they're called tag divisions, where the tag is outside of the interval, and therefore it's harder to be McShane integrable than it is to be Lebesgue integrable. So that's why it's harder to be McShane integrable than it is to be Henstock-Kurzweil integral, and that's why you end up with this smaller integral. Okay? That's the only difference. All right, so I apologize, kind of low here. The Riemann integral is contained in the Lebesgue integral, but not equal to it. The Lebesgue integral is equal to the McShane integral. And then the McShane integral is strictly contained in the gauge integral or the Henstock-Kurzweil integral. All right, all right. I'm going to just go quickly over this because it's not a huge part of my discussion. But another way that you can get an integral, which is even more broad than that of the Henstock-Kurzweil, is to talk about the approximate Henstock-Kurzweil integral. And so look at the bottom here, right? In the case of the Henstock-Kurzweil integral, we require that the tagged interval satisfy this, but we allow any, okay, we allow any endpoint to be the xi minus 1 to the xi, right? So I fix my, so essentially the difference between really the Riemann integral and the gauge integral is the Riemann integral, you set your interval and then the gauge, the tag, the point that we evaluate the function can be anything inside. Here's the other way around. Here you fix the point and then the endpoints of the intervals are governed by the gauge, right? Well, what if you don't allow all of the points in this interval here to be endpoints, but only most of them, right? Then you would get, sorry, then you would get something called this approximate gauge integral, where most but not all of the points that are in that interval can serve as the endpoints. It's strictly wider. Again, not a big part of the discussion here, but I'm going to come back to it later because we needed this to be able to find some of our results. All right, so now we have this approximate gauge or approximate Henstock-Kurzweil integral, which is strictly bigger than the gauge integral. My bad, my mouse is a little bit messy here. Again, more for historical reasons. There is another type of integration process, which was developed by Oscar Perron. Sounds French, but I think he was German. Okay, and his idea was to talk about derivatives. What's a derivative? Okay, so we see here that if I take this difference quotient here, right, and if that thing here were to approach a particular value as y goes to 0, y goes to x here, we would say that that value is the value of the derivative. Okay. Well, there's a difference between, on the one hand, a limit, and on the other hand, what's called a lim sup. All right, and a lim inf. Yeah. So of course, if the lim sup and the lim inf coincide here, then we have a limit and we have a derivative. So again, if you give me a second here to pull up a Desmos, I want to show you a good picture of an example of a function that has a derivatives, but not a derivative at a point. And let me see. No, I got to pull up here. Go. And I got to get my other Desmos here. Sorry. There we go. This guy. Can you see it? It looks like a big X, kind of, sort of. So it's X times sine of 1 over X. Right? Well, we can see that the schmear here, the schmear in the middle there, is simply that the the function is oscillating so rapidly that the thickness of the graph kind of runs into its neighbors here. So you get this kind of schmear. But I think you can imagine that, right? On the right, the line y is equal to x is going to be attained infinitely many times by this function in any interval about 0. And the line y equals minus x is also going to be attained infinitely many times. Okay, so in this case, we would say the upper derivative, both on the right and on the left, is 1, and the lower derivative is minus 1. Because, right, it never gets below minus 1, because this is y equals minus x. And so the derivative is never lower than minus 1, because the graph never lives outside of this kind of x, right? It always varies between minus 1. So the value, the difference quotient is between minus 1 and 1, and it actually attains those values, right? Now, can I pull this thing off? I think so. All right. All right. So derivatives are a big deal. When you have functions that fail to be differentiable, you sometimes have to just deal with the derivatives. Okay. Again, don't want to spend a ton of time on this, but Perron's idea, again from 1910, we're talking about all of these mathematicians, Lebesgue, Perron, and then there's also Donjois, lived around or worked around the 1910 times, and Henstock much later in 1960. Right? So his idea was to consider what are called major functions and minor functions. And what he was saying was that we want to have, say, a major function has the property that its lower derivative is greater than or equal to x, not its derivative, right? Because the idea is that, most of the time we think of a function whose antiderivative has a derivative equal to f everywhere. Well, maybe we can't get that, but at least we want to have something that approximates. So we have this major function, the lower derivative of u is greater than or equal to f. The upper derivative of this v is less than or equal to f. Okay, I don't know why this thing came up top here. RE stands for extended reals, so we do allow the function f to be infinite at some point. It turns out it has to be 0 except on a set of measures 0. It has to be finite except on a set of measures 0. Right? And the basic idea is that if you say that the u of a is equal to 0 and the v is equal to 0, u minus v turns out to be both non-negative and decreasing, and it kind of provides kind of an envelope. And then if we squeeze these two together, if we take the infimum of all the u's and the supremum of all the v's, if those guys coincide, then we have something called the integral. Right? Again, I'm really, this is just for historical purposes. I need to talk about all this so that you can kind of set the stage. We can set the stage, but I really didn't work along these lines. I worked along the lines of developing a Henstock-Kurzweil type integral.
So this is like the fundamental theorem of calculus in disguise.
Essentially, yeah, absolutely, yeah, essentially, yeah, right. And it's taking into account this u and the v are not, they're not actually the derivative, right? They could be, it could be that maybe the function just fails to be differentiable at some points, and so the best you can do is come up with these major and minor functions, right? All right, the Perron integral and the Henstock-Kurzweil integral are equivalent. They integrate the same functions. Each integral gives the same value, right? You can actually put some restrictions on the gauge functions. You can require them to be continuous, and you can even allow these inequalities to fail on a countable set. So I'm hoping students, you've had some idea of a countable, something you can count, like a sequence. Uncountable is like the whole interval of points. That's an uncountable set, right? You cannot possibly count all the real numbers between 0 and 1, say. Right? There's a big difference between countable and uncountable. So countable, we can handle. Uncountable, we cannot handle. There's a lot of bad things that happen. Allow this to fail in an uncountable set. Right? If you put an even stronger condition on these major and minor functions, require that they be absolutely continuous, and I'll talk about what that is in a minute, you actually get the Lebesgue integral. So there's another way of playing with the definition of a Perron integral to get the Lebesgue integral. For the Henstock-Kurzweil, we change the way we define our intervals, that are tagged intervals. We don't require the tag to be inside the interval, and we get the Lebesgue integral. And there's another way we can go from Perron to Lebesgue in a natural way, okay? Right? Okay. There is a Perron approximate integral. Again, we can't do everything. But now comes Sagar and me. Finally, we enter the stage. We started working together around 2000. And then I graduated in 2012, and I think we ended up publishing this paper in 2013 in Studia Mathematica. Right? So far, what I'm trying to say is that Lebesgue is smaller, and Henstock, Kurzweil, and Perron are larger but equivalent to one another. Right? And then there's this approximate Henstock, Kurzweil, and approximate Perron, which are also equivalent to one another. This has been known for many, many years, at least a century. Now, what was unexpected was this. Right? So Zygmunt was Fabes's advisor, right, and Sager's advisor, right? The advisor of just a whole lot of interesting people, including Calderon himself. So Calderon was a student of Zygmunt's and then eventually became a very famous professor and is Calixto Calderon's half-brother from UIC. I never met Alberto except to see him at a lecture, but I knew Calixto pretty well. So in 1961, the year before I was born, it's a long time ago, the Calderon and Zygmunt defined a derivative in LR. So I just put them right next to each other. This, of course, is the derivative, classical derivative. We normally would say that the limit of this ratio here is equal to alpha, but we can just as well say that the difference between these two goes to zero. It's the same thing. It's just easier for me to go from this step to this step. So the LR derivative means that we take the integral, but we average it, right? We take this difference, the difference between the difference quotient and alpha, we raise its absolute value to the R power and take its average. Okay? It's pretty clear that the classical derivative would imply the LR derivative. If something is derivative in this sense, it's essentially the case of R going to infinity. You end up with R infinity norm, L infinity, instead of a particular R, right? But it is more general. Okay, right? Okay. So again, for historical purposes, I just want to mention this, but Louis Gordon was also a student of Zygmunt's. Wilfred, did you ever meet Louis Gordon? I don't know if he's at UIC for many, many years. I think he started at the Navy Pier campus and went to the main campus. He took 20 years to write this paper with Zygmunt. So I consider this to be really one of Zygmunt's very, very excellent works. I've read it many, many times. And the idea is that Zygmunt said to Sager, he said, with Louis Gordon, we were able to make some results. We were able to get some results. But what he really wanted to do was to figure out a way to come up with an Henstock-Kurzweil type integral that would integrate these LR derivatives. And that's the project that Sager eventually gave to me. So in 1967, quite a long time ago, Louis Gordon had developed this Perron type integral that integrates the derivatives that are defined in this manner, right? Just like the Henstock-Kurzweil integral integrates and the Perron integral integrates all derivatives defined in the classical sense. Okay, right? Now, right? This is Sager and me, right? What we did was we developed an integral which integrates also all LR derivatives. And the way we did it was a little bit backwards, or maybe a little indirectly. We said that, all right, the function is integrable if there exists a function, capital F, satisfying this for all delta fine tag partitions, right? There was a lot of stuff that we weren't able to figure out. Okay, we knew that this F was unique up to an additive constant, right? And we knew that the PR integral was contained in the HKR integral, but we didn't know if the HKR integral was contained in the PR integral. Have y'all met Marshall Ash, J. Marshall Ash from DePaul? Did you ever meet him? No? He retired a number of years ago. Well, anyway, he was on my thesis committee. He almost didn't pass me because he said, "Why didn't you figure this out?" I said, "We couldn't figure it out. We spent years." But Steve, did you know him? Because he was at a lot of conferences. He was at a lot of conferences, and he was at there was a Loyola AMS regional, and he gave a talk there with a couple of others. So anyway, so he was pretty ticked. And I'm very happy to say that we were able to figure it out much, much later. So I did email him. I don't know if he ever got it, but we were never able to show that the HKR integral was contained in the PR integral. So it was a gap, but there's no sin in finding out that it's strictly contained. The sin was that we hadn't figured it out one way or the other. We left it open, and it was open for many years actually. So from the time this first paper was published to 2021, 17 years, it was unknown. And, the world had a crack at it. They had a chance to figure it out. No one ever did figure it out. But the answer is no. But in order to do that, we had to bring in a very heavy hitter, Valentin Shkvatsov, who is master of. So his advisor was Minchov, who was and Minchov was a student of Kolmogorov. I mean, he's got a pedigree. This guy's got a pedigree. So at Moscow. So with Shkvatsov's help, because when I first mentioned this problem to Shkvatsov, he immediately thought, no, they're not equal. He immediately thought that because I always thought they were equal, and I was trying to show they were equal. Turns out that they were not. Well, knowing that it isn't makes it easier because I was beating my head against the wall against a problem that I could not solve because it was unsolvable. So I was trying to figure out a way to show that the HKR integral was contained in the PR integral. Turns out that that's impossible. The Proceedings is not a bad journal. So, I mean, we were very happy to get something published into the Proceedings in 2022. Okay, so what really should probably happen now is that maybe one of these integrals needs to be redefined. Maybe we need to shrink the HKR to make it conform with the PR, or maybe we need to define the PR a little differently to expand it to meet the HKR. In other words, one of the integral definitions is probably not right. I think ours is right for a number of reasons. But at this point, we know that the PR integral functions and the HKR integral are separate. And so if you prove something for the PR integral, it's not necessarily true for the HKR integral. And that caused us the ability to write a number of papers. Okay, I only have a few minutes left. I'll try to get done obviously by 2:25, let's say. But next we talk about descriptive characterizations, okay? So to define the Lebesgue integral, it can be quite complicated, starting with simple functions and then some limit theorems. But an easy way to do it, which I can write right here, and it's just 3 lines, is to talk about the antiderivative, or the indefinite integrals. So a function, right, little f, is Lebesgue integrable if and only if there is an absolutely continuous function, all right? Okay, this is absolutely continuous function. This is the definition of it, whose derivative is equal to little f, and it's in almost everywhere except on a set of measures 0. Okay, so what's the difference between continuity and absolute continuity, right? So continuity is at a single point. Continuity is a property at a single point. And even uniform continuity does not imply absolute continuity. We do know that if a function is continuous on a closed interval, it's actually uniformly continuous. But there's something called the devil's staircase. I don't know if you've heard of the devil's staircase or the Cantor-Lebesgue function, which can rise from, right? It can rise from 0 to 1 or to any constant, despite the fact that its derivative is 0 almost everywhere. It's like it shouldn't happen, but it does happen. But that function is not absolutely continuous, right? So absolute continuity would knock that possibility out, right? So the idea is that you basically take a collection of intervals, they're not overlapping, but their sum is small, it's eta here, right? Under that condition, then the sum of the vertical displacements can't be small if you have absolute continuity. Okay, so this is the characterization of Lebesgue integrable functions. Much stronger than continuity, much stronger than continuity. You need an absolutely continuous function. Now, automatically, my top comment here, automatically, you can easily show that an absolutely continuous function is bounded variation. Bounded variation, it's the difference of 2 non-decreasing functions, and it can easily be shown that non-decreasing functions are differentiable almost everywhere. And so the AC functions are clearly differentiable almost everywhere. Okay, so automatically you have this property. Okay, this is a Luzin descriptive characterization, Luzin type. So Luzin was the one who came up with this characterization, and it's not going around the definition. I mean, it turns out that the functions that have this property are exactly the ones that are integrable in the sense of the measure theoretic definition. Okay, so what we tried to do was we tried to figure out, Sagar and me and then others, we tried to figure out if maybe there's a way to give what are called descriptive characterizations of these other integrals, meaning that we give characterizations of their indefinite integrals instead of defining how we're going to, manipulate the function to get the antiderivatives or the indefinite integrals. What are the properties that the integrals have to have? Okay, so, all right, how do you guys remember Alex Caruso? I so miss him. So I named an integral after him, AC Fresh, and it's kind of a joke integral, but the idea was that, all right, and this is for students, this is for all of us. Okay, how do you go fishing for new ideas? Because, right, it's hard enough to do math. It's really hard if you don't even have an idea. So you got to have an idea. So the idea is to say, well, let's try to change the definition a little bit. Let's manipulate the definition. And what if you said that, so the original function, the original AC function had this brown stuff. And a freshman might say, well, just cut out that, just get rid of that. Just cut that out. Just leave that, take that out. Just forget about the eta and see what happens. Well, unfortunately, if you look at it more than a second here, you'll see that this turns out to say that the variation of the function, because you're not requiring that the intervals add up to small amount, this is saying now that the variation of the function has to be zero, arbitrary less than arbitrary epsilon. And if the variation is less than arbitrary epsilon, the variation is zero, and so it's a constant. So that's not a very interesting class of function. So that's not something you want to play with. You still want to have some sort of an eta, so this is what an eta condition. You still want to have that the intervals that you are evaluating shouldn't add up to too much. Okay, so we don't want to tamper with that. Right. So let's review the HKR HK integral function here, right? And we see that there actually is a way of describing Henstein-Kurzweil integral functions in terms of a class called AC delta. Okay. Now, I just crossed off the brown, and I'm going to just make it black now. There's the definition. But this is to show you the difference between AC and AC delta. But anyway, here it is. Now, what I want to point out is that there are two restrictions here. There's the delta and there's the eta. Okay, so the eta clearly is there so that you can't have all the intervals in the entire interval. You can't have all the subintervals. You have to take a small collection that doesn't add up to much. But you can't just take anything. You have to also make sure that they are delta fine. So what does delta fine mean, right? So that means that II is just an interval and XI is the tag here. And so that just means that II has to fit inside the interval from XI minus its gauge to XI plus its gauge. Okay, so it's what I call a belt and suspenders approach. So I just found this guy. I thought he looked good looking guy. Belt and suspenders is usually a criticism, right? You're too cautious. Belt and suspenders means you are so afraid your pants are going to fall down. You have both the belt and suspenders. You have redundancy essentially. So the question I had was, is there redundancy in here? Well, the answer, no, there's not redundancy in here. It turns out that given the definition of AC delta functions on an interval, AC delta and AC are the same. It's an exercise in Russell Gordon's book, very nice book. And it's an exercise to show that the gauge doesn't make a difference. It does make a difference if you come up with something called ACG delta, right? So if you take if you take your set E, whatever it is, and you break it into a countable union of sets, and if you say, well, my E is a union of sets on which F is AC delta, right? That is the class of functions which characterizes the antiderivatives or the indefinite integrals of Henstein-Kurzweil integral functions, right? Okay, so and those are automatically differentiable almost by definition, or by you don't have to add an extra. So it's belt and suspenders approach. You have a gauge and you have an eta, right? Okay, right. So someone might say, oh, well, right, now that I've got two things, right, I've got a gauge and an eta. So the wise, of course, is now the sophomore, because sophomore is a wise fool. And I was a very wise fool, or I was a foolish wise guy when I was a sophomore. So I'll go from freshman to sophomore here, and I'll have my AC wise function. So a little bit smarter. He says, well, let's get rid of the eta now. Okay, this time it doesn't. There's nothing, right? There's like even x itself would not be ACGYs. You have to have that polynomials should have these properties because those guys are all infinite Riemann. So that's too restrictive. So you gotta leave the eta in there, right? So it turns out that no, they're actually both necessary. The eta as well as the gauge. All right, so I'll go back to LR differentiability. This is just a different characterization of it. Okay, right? Either way, you can use the definition I have here or the definition on the previous slide. Okay, right? So we have this integral. Okay, and then what we did, very happy, right? We were able to come up with a class of functions which almost characterized the indefinite HKR integrals. Okay, so if you read it very carefully, right, that's the definition. Okay, and it's kind of what you'd expect it to be. This is why I think we have the right definition here, because this is kind of what you'd expect it to be. You just kind of change the absolute value of f of y minus f of x to these LR averages. So that's our guy. Okay, and a function is HKR integrable if and only if there exists f, which is ACGR, that we developed, such that its LR derivative was equal to f almost everywhere. Now, AC functions automatically have a derivative almost everywhere. ACG delta functions automatically have a derivative almost everywhere. We did not know. We simply did not know. We worked at it very hard. We did not know whether or not ACG, our functions, have an LR derivative almost everywhere. So there was a gap. There was a gap. Okay? Definitely a gap. 2023, with the help of now all four of us, Swarovski is in Bydgoszcz, Poland, and he has been a member of the Real Analysis Exchange group as long as I have. So we've known each other a really long time. He's a real expert in integration theory. The four of us together were able to, yes, come up with the.
Could you repeat what is the gap?
So, all right, it's up here. Okay, right. I say, what did that happen? Okay. I say that a function is integrable in this sense if and only if there exists an f, which is ACGR, having this property. So you have to have that as an extra stipulation. You have to say, number one, f is an ACGR function, and number two, it has an LR derivative almost everywhere. That's not what you would expect. You would expect that whatever the ACG, whatever the absolute continuity condition is, it should have the correct definition a priori without an extra assumption. We were able to, in 2023, show that ACGR functions do possess this derivative almost everywhere. So you don't have to make it as an extra assumption. Okay, which is now we know we have what's called a complete characteristic descriptive characterization. Right? There's many other cases where we have these AC type functions and they characterize the indefinite integrals in whatever sense. But they have to have the differentiation property has to be a consequence of the definition. We didn't know if it was the case, but now we know it is. All right? Approximate differentiability. I'm going to skip over this because I only have a couple of minutes. These are Piotr's things. I don't know much about those, but these are Piotr's things. He loves these things. But anyway, because Wilfredo is here, I promised I'd do something about trigonometric series. So we have a wonderful result on trigonometric series. Okay, so this is Bourke-Hill's integral. I think that it's worth looking into this this idea. Right? I don't have the definition of Bourke-Hill's integral, but Bourke-Hill defined an integration process so that, right, okay, as long as this thing here converges almost everywhere, okay, to what we call a CP integrable function, right? Now, right, that in itself is not enough. You also need that the partial sums, even though they may fail to converge, they at least need to be bounded on now on the complement of a countable set. So that means even on the set of measure 0 where you don't have convergence, you still have to have reasonably good behavior. Okay, then you can recover the coefficients by simply doing what you normally do, right? You integrate them now with respect to the CP integration process, right? So what Zygmunt wanted to do with Louis Gordon, he's passed away now since the 80s, but he gave this project to Sagar, who gave it to me. And what he wanted to do was to essentially prove something like this for the PR integral. And I don't think he ever did, but we were able to do it. So first we were able to simply say that if the function is PR integrable, then it is CP integrable, and we could change PR to CP in both of those places. That was one paper. That was in JMAA, a good journal. Then we extended further. But how did we do it? Okay. How do we do it? We had to change the definition of ACGR in order to be able to do it. And what essentially Valentin realized was that the ACGR process was belt and suspenders. I don't have a suspenders here. I'm not going to show you my belt, but I showed you what I'm talking about, right? There was a gauge and there was an eta. And we realized that in order to show that HKR integrable functions were also CP integrable, we had to get rid of the gauge. We couldn't figure out how to handle the gauge. So it turned out that, right, if ACGR functions had a gauge, we were able to develop a class of functions called ACGR star functions where gauge does not appear. So the gauge was taken out. And we ended up with the same class. So we ended up with a simpler characterization. Okay, simpler characterization. There's no need to mention the gauge, right? So it turns out that the belt and suspenders were not both necessary, just the suspenders. I love this. So you didn't need both. So it really was a belt and suspenders problem. Okay. So because of that, we were able to show that the HKR integrable functions and therefore the PR integrable functions of Louis Gordon and Zygmunt from the 1960s were CP integrable. So we get this result. I'm simply saying that in the three cases where CP appears, we can now substitute HKR. Why do we care? Well, if you are able to determine whether that a function is HKR integrable, and you didn't know that HKR integrable functions were a priori CP integrable, you would not necessarily have this coefficients problem. You would not necessarily have this theorem. But now we know we do. So I think that we are honing in on what Zygmunt was trying to get at in the 1960s by coming up with this LR derivative and then trying to find an integration process which inverts it. Okay, um, these are my my suggestions for you. Work with a good team. Everybody brings good strengths. Math can be very lonely, as you know. It can be very lonely. It's good to have a surprising result. Man bites dog is more interesting than dog bites man. I think that if we had shown that the PR integral was equivalent to the HKR integral, they would be like, yeah, well, should be, but it's not. And since it was surprising, the editors were like, yeah, that's interesting. And finally, if you make a mistake, because we had some gaps, they weren't really wrong. Okay. One thing we're working on right now is a better proof that the indefinite HKR integral is unique up to an additive constant. We have a better proof and we've submitted it for application. And the only reason we came up with this better proof was because I was embarrassed to put it in the book. So we need to fix it. Some references. Now, this group here is Chicago 2008. So in 2008, so now 17 years ago, all these people traveled to our humble city for the Real Analysis Exchange Summer Symposium. I'm in there. I don't exactly know where I am, but I'm in there. And you might know some of these people. I don't know. Uh, uh, this is Bruckner here. Wrote a very famous real analysis text, and Bruckner. And this is Cliff. This is Jack. Where's Cliff Weil? Oh, Cliff Weil is there somewhere. There's a number of people that you probably have heard of. This is Paul Humpke here. He's the still the editor of Real Analysis Exchange. So there's some really good people in this group, and it's a really nice it's a nice group to get involved with if you're at all interested in real analysis. And that's all I have for you. Thank you for your attention. Any questions? Thank you.
Thank you very much, Paul. A beautiful talk. Especially, Riemann formulate his Riemann integral notion in his memoir for studying Fourier series.
Oh, I didn't know that. I did not know that.
Yeah. So,
Yeah.
and here you do the same. At the end,
Yeah.
you use your integral
Did
to
not know
go
that.
back to Fourier series. So that,
Beautiful.
yeah, I really love that.
No, it's
Okay, any
great.
question or comment?
I've got questions. You have like there's a lot of stuff in here that just like is firing neurons off in my brain. And a lot of times I see a lot of cases where you have like integrals, where you're averaging over the length and a function minus its value at a point that just makes me feel like Poincare inequalities might spring forth out of that. Did that come up at all in your work?
I'm gonna have to look that one up. I'm sorry.
Okay.
I'm just not familiar with it. So I'm going to look. I promise you. Poincare inequalities. I'm going to look tonight. It
So the
just never
Poincare
came up, but it's never came up. But I'm gonna. It might lead to something because these little chance comments can lead to avenues of research. Thank you very much. I will definitely look into it now. I'll let you know what I find when I see you in the hall.
And are you doing
Thank you.
like RN, or have you looked at other spaces or manifolds, or I
That'd be
look
really
at weird spaces,
yeah.
look other things like so
Right.
for background, when I was working on my thesis a long, long time ago, I was looking at weird spaces and some of the things we would do to try to see, well, what can you do about a gradient is an idea of an upper gradient. So it's something where instead of like the fundamental theorem of calculus with an equality, you've got an inequality. Um, so a function has an upper gradient if it has a function that, you know, uh, the integral of it and the upper gradient is sort of on the one side, and you've
Sounds
got
like a major function. Sounds like major and minor functions.
similar to
Could
that.
be. Could be.
But
Yeah.
you could have tons of upper gradients for a function. So if it had an actual gradient, that'd be that, but it could do stuff for others. And you could use this in weird spaces where you wouldn't
Yeah.
necessarily have the nice continuity. I don't know. It feels like these ideas kind of like could tie together somehow because there are a lot of things to make, make up for weird spaces, but then you've got something to make up for functions that are more like pointwise continuous instead of absolutely continuous, sort of that sort of conversation. And do these things sort of fit together somehow? I have no idea. I'm
No,
just
thank you.
general questions. Sorry.
Other question or comment?
I think he froze. He froze.
I have a question and a request because I mean there is a lot of information in those slides. So the request is whether you can share the slides. That would be wonderful. And the question is, in some parts of what I could follow, there was some average. You have the integral and you average that with the length of the interval. So since the maximal function is the supremum of that, cannot you use some maximal function techniques there or something like that? Oh,
We lost him. He had
it disappeared.
I'd ask questions and I saw him like
What?
which was like a frozen face because the internet froze and
Yeah, it probably.
I think
Yeah,
internet issues,
he
but
warned us that could happen.
ask him about his slides. Have him send them. I want to look at them. There's a lot of good stuff in there. Then I can grill him.
Okay, let me stop recording.